Good morning, everyone. You're all doing well. So, a couple things to note. Very well. Very good. A couple things to note. I'm not as well as you are, but good for you. So, a couple things to note. Your second test is going to be this weekend. Now, I have it stretched an extra day, so you guys will have Sunday to, oh gosh, I believe it was Sunday to Tuesday. Let me just double check on my end, but I'm almost positive because I know that the 4th is on Sunday. So let's see, where are you? Testing. Yeah, Sunday it opens at 5 a.m. and Tuesday it closes at midnight because Sunday is the 4th and then Monday is the day after the 4th, which is for some people about as worthless. You're about as worthless on the 5th as you are on the 4th. So you do have until Tuesday. If you want to get it done on the 4th before all your celebrations, that would be a great idea. I always recommend doing things earlier than later, but let's be real, when I was in college, I procrastinated everything. It was very last minute. I needed that fire under my butt to get it done. So we are going to actually, if you want to know, my last year or my last semester as a grad student, I was sort of like, I had like dilly-dallied the 2 years before. I mean, I'd gathered my research and stuff, but was just like sort of dragging my feet on writing my thesis. And my advisor was like, hey, I'm taking a sabbatical for 6 months. So you either need to get your thesis done and defended in the next 3 weeks, or you're going to have to wait a year. I go, oh my gosh. So I wrote a 100-page thesis and defended it in a 3-week period. And that was one of the most insane things I have ever done in my entire life. And also having children. That's also pretty insane. But anyway, if you can get the test done early, get the test done early. So we are going to continue on with chapter 9. We did a good amount of it last time. So I think we'll be able to get through 9 and then start 10. And then on Thursday, we can do chapter 10 and some of chapter 6 so that the following week we can have maybe a little bit of a break. So just to sort of bring it all together, I want you guys to do an example for me. Write the electron configuration. Oh, man. I have my table or my periodic chart. Let me pull one out of the text. Okay, I want you to give me the electron configuration, the full and the abbreviated. Okay, for let's do bromine. Okay. Halogen, number 35. Give me the full electron configuration and then go ahead and do the abbreviated. I'll give you just 2 minutes for that. Shouldn't take too long. All right, so bromine is number 35. We look at periodic chart. It sits 1, 2, 3, sits over right here. Okay, so in order to get to this configuration, we have to piggyback off the configuration of every element before it. So we're going to read across like a book. So first we do row 1 in the S block, then we do row 2 in the S block, then we move into 2P, so on and so on. So the ordering for this guy should be 1S2, 2S2, 2P6, 3S2, 3P6, 4S2, 3D10. Remember, the D's are always one less than the S and the P around it. 4P5. We don't get the full fill of 6 because we're not krypton, we're bromine. Now, if we want to do the abbreviation for this, bromine, the noble gas that comes before bromine is argon. You can't abbreviate it with the noble gas that comes after it because we don't have enough electrons. So that is going to encompass all of this. So this whole chunk here, we can abbreviate with argon, put it in brackets. Then I need to make sure that I add everything that comes after that. Otherwise, we just have the configuration for argon. So we've got 4s2, 3d10, 4p5. Any questions on that from last time? Okay, so let's move a little bit forward with that chapter then. Okay, so the next thing that we'll get into is talking about electron configurations as well as far as its relationship to the periodic chart, and then also these things called valence electrons and core electrons. So a valence electron is an electron that is in the outermost shell, or the shell that has the highest principal quantum number. And so if we had, let's say, for instance, we go back to bromine's configuration here. Okay, the highest number that we have is 4, right? We don't include the D. These are called core electrons. We would look at the highest number, so 4 and 4. There's 2 here, and there's 5 here for a total of 7 valence electrons. Okay. Again, a valence electron is the electron in the outermost shell. Why is that important? Because these are the electrons that are used in bonding. So bringing compounds together, why two things like come together. Electrons in the core, or core electrons, like all the ones back here in the argon configuration, and then this D here, those you're not going to use for bonding. They're too like far in the onion layers. They're too close to the nucleus to use in any sort of chemical bonding. So electrons are important because they allow things to come together. That's why we have things like H2O or CO2 and all that stuff. Electrons that are not in the outermost principal shell are core electrons. So silicon, Si, this is its electron configuration. If we look just at the 3s, we can see that we have 2 in the S and 2 in the P for a total of 4 valence electrons. Look at where silicon sits on the periodic chart. It is in a main group and it is in column 4. How many valence electrons does it have? 4. Okay. Let's look at selenium. Selenium has this electron configuration here. Now it has some funky d orbital ones but we consider those core electrons. We only look at the highest number. So the 4 here and the 4 here. There's a 4s and a 4p. 2 here and 4 here for a total of 6 valence electrons. Okay, look at where selenium is on the periodic chart. It is in column 6, and there are 6 valence electrons. So for all the main group elements, that means the 2 columns on the left and the 6 columns on the right, whatever column number they are in is how many valence electrons they have. So you don't necessarily have to like draw the electron configuration out and count it all up. It just correlates to whatever the column it's in, because each, like nitrogen, for instance, if we look here, nitrogen is in column 5, and it has 5 valence electrons, 2 in its S and 3 in its P. Well, what about phosphorus? Phosphorus also has 5 valence electrons. It has 2 in its outer S and 3 in its outer P. This just happens to be at the level of 2. This happens to be at the level of 3, but it's still following the same sequence. So column 1 here, 1 valence electron. Column 2, 2 valence electrons. Column 3, where we have boron and aluminum, 3 valence electrons. 4, 5, 6, 7, and then column 8, outside of helium. Helium has 2 valence electrons, which in this case is stable, but all the other ones have 8 valence electrons, which is a stable configuration. So, if you have 8 valence electrons, you don't want any electrons, you don't need any electrons, and you don't want to get rid of any electrons, so you're not going to do a whole lot of bonding to make that happen. So I'm going to give you just 3, and real quick, I just want you to tell me, or can figure out how many valence electrons does it have. So calcium, phosphorus, bromine, and neon. Tell me how many valence electrons each one of these has. Don't draw the electron configuration. Just look at the column it's in. Okay, so calcium is in column 2, 2 valence electrons. Phosphorus is in column 5, 5 valence electrons. It's really that easy. Bromine, column 7, 7 valence electrons. Neon is in that last column, so 8 valence electrons. If I had given you something like iron, iron is not a main group element, so how many valence electrons it has, how many valence electrons does it have, depends. Remember how we said that the transition metals can have varying charges? If they can have varying charges, they can have varying number of valence electrons, so it depends on that. All right. So this whole section is talking about the pattern of the periodic chart, which we've already gone over, the S block, the P, the D, and the F block, right? S, P, D, and F. Remember that D is 1 less than the P and or the S and the P around it, and F is 1 less than the D it's next to. Okay, so you step down 1 energy level as you fill. So like for instance here, if we were at barium, it would be the 6s, the 5d, and then it would be the 4f. So 6, 5, 4. The P though stays consistent with the S. So the number of valence electrons for any main group element minus helium is whatever the column it's in. We've already talked about this. There are some weird electron configurations for a couple different elements. So I want you, off of what you know right now, I want you to write the electron configuration for chromium. The full one, not the abbreviated. Okay, so for chromium, off of what you guys have done so far, you would go with 1s to 2s to 2p6, 3s2, 3, no, 3p6, 4s2, 3d4, right? That's kind of what we would, 1, 2, 3, 4, yeah. So why is this not the actual configuration? The actual configuration is slightly different than this. I'm going to draw out these boxes right here, like the orbital diagrams. So for the 4s, I'm not going to do all these ones because they're all full. We'd have a box like this, and we'd have an arrow up and an arrow down. The 3D, we would have a series of 5 boxes. 4, 5. And off of this configuration, it would look like this, because we fill them in singularly first and then double up. So d orbitals like to be half full or full. They don't like to be partially full like this. So if they're really close to being full like this, what will happen is that one of the electrons from this s will move over here, because it's more stable to look like this, 4s, 1 electron there, and then a single electron in each of these boxes like this. This is a more stable configuration than this is. So the electron configuration for chromium is actually going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Okay, the 1 electron from here moves to there. This one moves to here. That happens anytime you have like a 4 on the D or a 9 on the D. If this was 3, we wouldn't necessarily move 2 electrons, but just like, you know, where we have chromium or copper, right? Copper would be almost full, so it would steal the electron from the S. So just know that there are some exceptions. There are other exceptions outside of that, but that is one where you see chromium and you see copper. If you're wondering, why is the S not full? It's because the half full D or the full D is more stable. So it's going to gravitate towards that. Cool. So I want you to do the electron configuration for sodium. And then I also want you to do it for the sodium ion. Okay, you got to ask yourself, how are these different? Then I also want you to do it for, let's do another coupling. We'll do it for sulfur. And then I also want you to do it for the sulfur ion. Their electron configurations will not look the exact same. Okay, they will be different because they have differences in electrons. All right. So if you're like, what did you want me to do? Well, what I want you guys to do is sort of start to see why these charges are predictable. So sodium's electron configuration, just straight up sodium. It's number 11, so it should have 11 electrons, right? So we should go 1s2, 2s2, 2p6, 3s, 1. Okay, this is with 11 electrons. What's the difference between sodium and sodium with a +1? It's down 1 electron, right? So this should have 10 electrons. So what is this thing going to look like? Well, it's going to be the configuration of sodium, but we're just going to strip off that last electron. So what is the configuration? 1s2, 2s2, 2p6. We just took that off. Right? It was just this part right here. You can count up the electrons. 2, 4 plus 6 equals 10. 10 electrons. So what is this configuration? This is equivalent to neon, right? Or we can say that the sodium ion is isoelectric with neon. It has the same electron configuration as neon. So why does sodium like to form this charge? Because when it forms this charge, it has a stable electron configuration. Would sodium ever lose 2 electrons? No, because if it lost 2 electrons, it would start eating into this stable outer shell. So it's not going to do that. Would it ever add electrons? No, because it would have to add 7 electrons to get to the next stable shell, right? So the easiest thing for it to do is ditch that 1. Let's look at sulfurs. Sulfurs, 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4. Okay. Now this thing has 16 electrons. This thing has 18 electrons, right? Because we added 2 electrons. So it's going to be the same configuration as this, but we're going to add 2 electrons. 1s2, 2s2, 2p6, 3s2, 3p. Instead of 4, it's going to be 3p6. This thing is isoelectric with what? It's isoelectric with argon. Everything wants to be like a noble gas. That's what they're all trying to do. They're all trying to become like a noble gas because that configuration is particularly stable. So is that making a little more sense why those the elements in the specific columns form predictable charges, like the main group elements? If we look at this thing right here, right? If I'm in this column, I like to lose an electron. Losing an electron will back me up to the noble gas before it. If I'm in this column, losing 2 electrons backs me up 2 spots to the noble gas before it. If we're over here on this side, right, adding a single electron pushes me forward to the noble gas right after me. Adding 2 electrons puts me forward 2 spots to get me again to the noble gas. 3 here, 1, 2, 3 spots forward. It's all working towards the noble gases. Okay, so any questions on that? On electron configurations? I know in the beginning of this chapter, it can feel like a little freaky and scary, and then hopefully it makes a little bit more sense now. You will need to be able to do electron configurations. You need to be able to do orbital diagrams. You need to know some of that stuff from the beginning of the chapter, not so much the history of the electron, but definitely like light, you know, the different wavelengths and things like that. So make sure you've got that down. And then this last part here is important. So if you don't have your periodic chart out already, grab your chart, the one that you have all your notes on, because we're going to talk about some trends that we have with the periodic chart. So the first one is atomic size. So the biggest element on the chart is in this lower left-hand corner. They put it as cesium, sometimes number 87, francium. People will call that one Fat Frankie because he's the biggest guy, okay? They are smaller as you move up and to the right. So biggest atoms, lower left, smallest atom, up and to the right. It makes sense that they're going to get bigger as you move down, right? Because what happens as you move down? You're adding a new electron shell. You're adding a new onion layer of electrons, and most of the size of an atom is just the electrons, right? The nucleus is super teeny tiny in the center. The electrons are what take up all the space. So if you're adding a new energy shell, you're going to have a bigger atom. This is a little bit counterintuitive, but the atoms rather get smaller as you move across the periodic chart. as you move across the periodic chart. So as we move from left to right, the atom is smaller than the one before it. Now, you may be wondering, well, but aren't we gaining electrons as we move across? We are gaining electrons, but we're gaining electrons within the same layer or the same shell. So, this here has one electron more than this electron, but they're in the same energy level. They're both in the 2 level. What also increases as we move across? The number of protons. And protons have a positive charge. So what are they going to do? The protons will actually take this 2 level and pull it closer to the nucleus. Okay, so the shell, the 2 shell, gets smaller as you move across because the protons increase and tug on it. You may be filling more electrons into that layer, but the layer itself gets closer to the nucleus. So biggest on the lower left, smallest on the upper right. Another thing we've got is ionization energy. Ionization energy increases as you move to the right across the periodic table and decreases as you move down. Let's pull this up. Okay. So the ionization energy is the lowest in the lower left-hand corner, and it's the highest in the upper right-hand corner. Now, what is ionization energy? Ionization energy is the amount of energy it takes to remove the first electron. So even if you are a metal, there's still a little bit of energy required to take away an electron. But these guys, like Frankie down here, he already kind of has this predisposition to want to get rid of electrons. And he's so big that that outer electron is like almost falling off. So it's really easy to grab the electron from him. Low energy, low ionization energy. Now, if we go over to fluorine, and this doesn't include the noble gases, kind of just think of it as fluorine here. So fluorine has a very high, actually this particular trend does include the noble gases, but up in this upper right-hand corner, these have high ionization energy, meaning it is going to be nearly impossible to pull an electron off of any of the noble gases, and it's going to be really hard to pull the electron off of fluorine. Fluorine's electron configuration is this: 1s2, 2s2, 2p5. There's no way I'm going to be able to get one of those off there and have 1s2, 2s2, 2p4. That's farther away from stability. So that's not going to happen. This is going to want to gain an electron, not lose an electron. I mean, can you force it? You could, but it's not going to naturally happen. The last property is metallic character. You kind of already know this, but metals tend to lose electrons in their chemical reactions. Non-metals tend to gain electrons. As far as how we characterize something's metallic quality, the most metallic things are in the lower left-hand corner where Fat Frankie is. The least metallic are in the upper right-hand corner. That shouldn't be anything new, right? You know where your zigzag line is, you work from there. So do know those trends, because you may have, a question that's like, what's more metallic, or put these in size of decreasing, put these in order of decreasing size, something like that. So no, down here, lower left, metallic, large, low ionization energy. In the upper right-hand corner here, we have non-metallic, small, high ionization energy. All right, and that's it for chapter 9. We're going to move into chapter 10. Actually, let's take a 5-minute break and then we'll move into chapter 10. So I'll see you guys back here at 10, 12, 10:15. So let's come on back. Get started, chapter 10 here. So this is sort of it can be kind of a tough chapter to teach remotely because we don't have any like ball and stick models. So we're going to want to be sort of using our minds to think three-dimensionally on how the shape of some of these molecules are. Some people find it useful to get like toothpicks and marshmallows to make some of these structures to help them sort of see what's going on. So, okay. All right. So bonding theories are these predictability models that help us to determine how like atoms are going to be bonded together and why they bond together in certain ways. So they predict what combinations of atoms will form certain compounds and which won't. Bonding theories help us to predict why salt is NaCl and not NaCl2, and why water is H2O and not H3O. Bonding theories also help us to explain the shape of the molecules, and that can give us a lot of insight into the physical and chemical properties. So the first part of this is Lewis theory, named after a dude named Lewis. When he drew structures of atoms, he would represent electrons as dots, and specifically valence electrons as dots that would surround the atom. These structures are really useful for predicting the shape of molecules. Lewis theory can determine whether a particular set of atoms will form a stable molecule, and also what that molecule will look like. It'll also help you if you bump into a place when you're like, that doesn't want to come together, that doesn't make sense. There are more advanced bonding theories than this one, but this is what we are going to use for class. It does a pretty good job. So in a Lewis structure, we represent valence electrons with dots. And remember from last chapter, the number of valence electrons of any main group element, except for helium, is equal to the group that they're in. Helium will just have 2 valence electrons. So here we have oxygen. Oxygen has 6 valence electrons. You could pull that off of the periodic chart with it being in column 6. They drew the electron configuration. That's not necessary, but you can see there's the 6 valence electrons. And this is what the Lewis structure would look like. Now, when drawing the Lewis structure, divide it into 4 quadrants. So like a top, side, down, and other side. You'll want to fill the electrons in singularly first. So dot, 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 dot. So it's balanced, and then go ahead and double back up. All right. You wouldn't want to do something like this, oxygen, where you put 2 here, 2 here, and then 2 here, and there's nothing on this side. That makes this whole thing kind of lopsided. Okay. So always fill in singularly like this. Oxygen, we put 1 on the top, side, bottom, side, and then go back and double up. You can start on the side, you can start on the bottom. It's a 3-dimensional structure. That itself doesn't matter. So each dot represents a single valence electron. Each side can hold a maximum of 2 electrons. So 4 sides, 2 electrons for a total of 8, which would make what we call an octet. An octet is very stable when all of them are filled. Fill the dots in singularly and then pair them up. There is one exception to this, and that's helium. Helium forms a duet. So when you're drawing helium, put both, not hydrogen, helium, put both dots on the same side like that. It's the only one you do that for. Make sure to follow this when you're doing the homework, or Mastering Chemistry will get mad at you. Okay, so here are the Lewis structures for the first set of elements, not row 1, but row 2. So lithium gets 1 dot, beryllium gets 2, boron 3, carbon 4. And you can see as you move on, you're adding a dot. You're increasing the number of valence electrons until you get over to neon here, which is just so pretty and happy and balanced. And that is because it forms an octet. And an octet is very stable. So everything is going to bond in such a way that they can become an octet. So write the Lewis structure for phosphorus. Now phosphorus has more electrons than the person above it, nitrogen, but they have a very similar Lewis dot structure, right? Here's phosphorus and here's nitrogen. 5, 5. Because remember, we're only including the outermost electrons. So even though phosphorus is one level up and has, a whole set of core electrons that nitrogen doesn't have, we don't include those. We just include the outer ones. Sometimes people will go, well, phosphorus is number 15, so it has 15 protons, so it has 15 electrons, so I somehow have to put 15 electrons around here. No, you just use valence electrons. The configuration for helium is this thing right here. It forms a duet, so put those 2 dots on the same side. Hydrogen also likes to form a duet. So hydrogen will gain an electron to try and get to this configuration. So in Lewis theory, a chemical bond involves the sharing or transferring of an electron to attain a stable electron configuration for all the atoms involved. So if 2 people or 2 atoms, I like personalize atoms a lot. If 2 atoms come together, both of them are going to bond only if they can both get what they want, which is an octet. If the electrons are directly transferred, so one's like, I don't want this, and the other one wants it, that's known as an ionic bond. They just give it away. If the electrons have to be shared, so one person's like, well, I don't really want to give you all of my electrons, but I'll let you have access to part of them. That's known as a covalent bond. Either way, whether it's an ionic or a covalent bond, you are transferring or sharing electrons to get to an octet. So a stable configuration usually consists of 8 electrons in the outermost shell, known as an octet. Everything wants to try and become an octet except for the very small guys. So hydrogen, and then also in some cases, lithium and beryllium, those guys will be okay with a duet. Hydrogen will gain an electron to become a duet. Lithium and beryllium will lose electrons to become a duet. So know that the very small guys at the very front of the or top of the periodic chart, they're okay with just 2. Everyone else, though, past that, go with 8. So when we have electrons transferred for ionic compounds, we're not going to use this theory so much with ionic stuff because you guys kind of already know how to do ionic. Like it's pretty easy to just flip-flop charges, right, to figure out what their setup's going to be. But to get a visual of it, we'll go over this, but I don't spend a whole lot of time on the test with this one. We tend to do more with sharing electrons. So when metals bond with nonmetals, there is a transfer, right? The metal will give up electrons, the nonmetal will take on the electrons, and we get a cation and an anion, and they stick together. The attraction is what bonds them together. So here we've got potassium and we've got chlorine. Potassium has 1 valence electron, chlorine has 7 valence electrons. Well, what does potassium want to do? Potassium wants to get rid of this electron. Because if it gets rid of that electron, then it has a complete shell from the previous set, right? If we get rid of potassiums, it becomes like argon. So potassium wants to give up the electron. Chlorine has 7 valence electrons. It's like, give me that electron, because then I'll have an octet, or it'll move forward to become like a noble gas. So this transfers over here. We end up with a positive charge and a negative charge, and they stick together or bond. Both have octets. Let's look at magnesium and oxygen. Magnesium has 2 valence electrons. Oxygen has 6 valence electrons. Well, magnesium likes to give up 2 electrons, and oxygen wants to take on 2 electrons. So these 2 electrons shift over here. This becomes a 2 plus charge, this becomes a 2 minus charge, and then they bond together and you get MgO, one of these for every one of these. What if we have a situation where we have like a difference in charges or just a one-to-one doesn't satiate it? So sodium and sulfur. In this case, sodium has 1 electron to give up. Sulfur wants 2 electrons. So 1 sodium can give an electron to sulfur, but it will only have 7. So what needs to happen is actually another sodium needs to participate in this and give another electron to give us a happy sulfur with an octet and 2 sodiums with octets. Now remember, how do we do this using the flip-flop rule? Well, we know sodium likes to form a +1, sulfur likes to form a 2-, flip-flop. We get Na2S. We were able to do that much faster than having to like draw the whole thing out. So for the most part, I don't know, I would stick with this when predicting formulas, but know that you can use the Lewis system to determine that. So this is where the money's at. So covalent Lewis structures, or this is where electrons get shared. When you have nonmetals bonded with other nonmetals, you get a molecular compound. And in a molecular compound, you get molecules, individual molecules, as opposed to like a 3-dimensional lattice structure, like in your ions. Molecular compounds have covalent bonds where everybody is sharing the electrons. They're very, very strong bonds. Okay, these things are hard to break up. In Lewis theory, we represent covalent bonding by allowing neighboring atoms to share some of their electrons in order to obtain an octet. The one exception, or there's also lithium and beryllium, but those are metals, so we wouldn't really see that. So the one exception is hydrogen. Hydrogen likes a duet. So don't ever give hydrogen 8. Give hydrogen 2, give everybody else 8. So let's look at this right here. We've got hydrogen and we've got oxygen. So we're not going to transfer. Some people would say, oh, well, I'm going to just draw this on my other whiteboard. I have more control there. So we've got water is H2O. We've got oxygen, which has 6 valence electrons, and hydrogen, and there's 2 of them. This is not ionic, okay? So I'm drawing this in red because this is not what's happening. The dot is not getting transferred over here. Why is that the case? Well, because hydrogen has 1 electron and then you take its electron away. Does it have any electrons to be happy with? No, it wants 2 electrons. Oxygen would be happy, but the hydrogens aren't happy. So hydrogen's like, no, I'm not going to give you my electron. I'll let you use it, but you've got to give me something in return. So instead, what happens is oxygen and hydrogen come to sort of a mutual agreement where they say, okay, I'm going to share this electron and you share that electron, and then we can make a bond, and the bond looks like this. It'll be a straight line. And so we're going to share those 2 electrons. Same thing here, this electron and this electron, let's share those electrons so that we both have access to the electrons. Nobody's getting more, nobody's getting less, and we get something like this. You can sometimes see water drawn like this, with 2 dots here, and then like an H and an H. Okay, this is a bond. It represents 2 electrons. Know that. Anytime you see a bar, that's 2 electrons. So now let's see what's happening. Oxygen has access to 2, 4, 6, 8 electrons. So oxygen is happy, right? It gets to play around with 8 electrons. What about hydrogen? Hydrogen has access to 2 electrons within the bond. It doesn't mean he gets them all to himself, but he at least has access to them. He's moved close enough where he can have both of them and sort of have like a quasi-stable situation. So these guys are now sharing the electrons. So here we go. They've drawn it here. We take the hydrogens and instead of transferring, we just move them together and they sit in the center here where they share. There's an overlap. So the hydrogen here gets to have a duet. The oxygen in the middle gets to have access to an octet, and everybody's happy. The shared guys here in this sort of middle area will get a line. Know the difference between bonding pair electrons and lone pair of electrons. So bonding pair electrons are electrons that are involved in bonding. Lone pair electrons are electrons on the center atom that don't include any sort of bonding. They don't have a buddy on the other side. Those are important to be able to find because they have an effect on the shape of the atom, or rather the molecule. So let's talk about why some of the things that are diatomics are diatomics. Remember, have no fear of ice cold beer or hydrogen, drop to nitrogen, go over oxygen, fluorine, chlorine, bromine, iodine. All those guys like to form duets. They bond to themselves. Why do they do that? Well, look at chlorine by itself. Sad chlorine has 7 valence electrons. How many electrons does he want? 8, right? So what if 2 chlorines, 2 adjacent chlorines, shared that one oddball together to make a bond? Well, now each one has access to 8 electrons. So when they bond to themselves, they are more stable. You can see here this chlorine has access to 8 electrons. This chlorine also has access to 8 electrons. Usually though, when you're drawing these Lewis structures, you don't just put the dots, you change it to a bar. It's easier to read which ones are bonded when there's a bar there. Hydrogen does the same thing, right? It's got a single electron here. It's not very happy with a single electron. So he's going to bond to another hydrogen so that they can share 2 electrons or form a duet. Oxygen is also a diatomic. It's a little bit different though, because it has 6 valence electrons. So it has 2 spots that like need to get satiated, right? So 2 oxygens will come together and they'll share not just one set of electrons, but they'll actually share 2 sets of electrons or form a double bond. And I will talk about how you can get double bonds. Don't worry just yet. Right now, just sort of trust me that this thing has a double bond. Double bonds are stronger than single bonds. Okay, so this bond with oxygen is stronger than the bond we saw with hydrogen. There is the situation where we've got our oxygen, and look, they both have access to an octet. This oxygen has 2 lone pairs and 2 bonded pairs. This oxygen, 2 lone pairs and 2 bonded pairs for 8 for each. Is this making sense? Okay. Nitrogen, also a diatomic, but he's pretty low on electrons. He only has 5 electrons, so they have to get really creative and actually share 3 sets of electrons in order to be stable. So there's nitrogen with 1, 2, 3, and then 2 on this side and 2 on this side. This is stable. Again, I will show you how to do all of this in a specific ordering. I'll give you a system. So this slide is really long, but it just pretty much says a double bond is stronger than a single bond, and it's also shorter. So the atoms will be closer together with a double bond. And then a triple bond is even shorter and even stronger than a double bond. The bond for nitrogen is so strong that it is actually really difficult to break an N2 molecule. And it becomes a relatively unreactive molecule. So nitrogen, like this, N2, is not going to do a whole lot of like combusting or exploding or anything like that because it's pretty happy and it's set up. So we're going to draw a Lewis dot structure. Those things that we saw, these right here, these are Lewis dot structures. We've got more than one atom, and we've got some bonds, and we've got some lone pairs, and we see how they're connected to each other and where all the electrons are. So there's a specific way to do this. First thing you want to do is write the correct skeletal structure. Okay, so we're going to do water. Even though we've done the water molecule, we already kind of know what it looks like. We're going to do that one. So when drawing a skeletal structure, you want to put the atoms in a correct sort of general vicinity ordering. There's a couple rules to this. Oxygen a lot of times likes to be a central atom. It's not always a central atom, but hydrogen has to be what's known as a terminal atom. That means hydrogen has to be on the sides. It can't be in the center. Why? How many electrons does hydrogen want? Hydrogen only wants 2 electrons. If you put it in the center, it will have more than 2 electrons. It will not be happy there. So make sure hydrogen's on the outside. This says here, the only way to absolutely know the correct skeletal structure of any molecule would be to examine it in nature. You'd need to have some sort of like really intense mass spec. So for now, just, you know, no hydrogens are on the outside. Another rule of thumb, molecules tend to be symmetrical. Okay, so they like to they like to be balanced. Nature likes to have a balance. So we're not going to see something like this, H bonded to H bonded to O, like that. That doesn't really work. Why? First of all, hydrogen doesn't like to be in the center. Second of all, that doesn't look very balanced, right? It looks more balanced if there's a hydrogen, an oxygen, and a hydrogen. Same thing if we had like, let's say we had SO3. I would put the sulfur in the center and the oxygens on the side. That looks more balanced than doing something like this. Sulfur on one side, oxygen in the center, and then like some other oxygens. Okay, that doesn't look very balanced. So keep it simple, keep it balanced, keep it neat. The second guideline has exceptions always. There's exceptions all over the place for this, but really the only things I'm going to test you on are going to be really straightforward. Okay, so follow the rules. So with water, I'm going to draw it over here, and this is the structure for water, and I'll show you how we can get to this. So first things first, draw a skeletal structure. We've got H2O. Okay, I'm going to put oxygen in the center and I'm going to put hydrogen on the side. I don't want you to do anything to it. I just want you to put the atoms in their relative place. Don't put electrons, don't bond, don't do anything like that. All right, step number 2, calculate the total number of valence electrons for the Lewis structure by summing up all the valence electrons of each atom in the molecule. So every atom, when it's coming into a molecule, brings a certain number of valence electrons. And those are what you get to play around with. So hydrogen is in column 1. So each hydrogen brings 1 valence electron. How many are there? There's 2. So make sure you multiply that by 2. Then we're going to add it to however many valence electrons oxygen brings. Well, oxygen brings 6 because it is in column 6. So how many valence electrons do I get to work with or play around with? 8. I have 8 electrons. I cannot have more than 8 electrons in this structure. I cannot have less than 8 electrons. Whatever you calculate here is the number of electrons that needs to be on the board. Okay? If you are happening to do this for a polyatomic ion, you need to take the charge into consideration when calculating it. So let's do that. We'll kind of do 2 simultaneously. So we'll do water and then we'll do sulfate. So I'll put water over here and then let's do sulfate over here. Sulfate is SO4 with a 2- charge. Let's draw the skeletal structure for sulfate. What do you guys want to put in the center? What would make it look like neat and clean and balanced? The sulfur, yeah. So let's put sulfur in the center and then we'll put 4 oxygens around it, kind of space them relatively even. Don't, you know, put like, don't do this. Have them sort of like clumped on one side. Try and stretch them out as best you can in 3-dimensional space. How many electrons do we get to play around with here? Well, we need to take this charge into account. So when it's a 2-, what does that mean? That means you have 2 additional electrons. So we take the valence electron of sulfur. Sulfur is in column 6, so that's 6 valence electrons. We're going to add it to oxygen, which has 6 valence electrons, but there are 4 of them. So you have to multiply it by the subscript or however many you have. If you have 4 oxygens, there are 4 times as many electrons coming. Then we're going to not subtract. I know it's like you see that negative and you want to subtract, but we're going to add 2 more because there's 2 additional electrons. So what is my overall valence electron charge here, or valence electron total here? It's 32 electrons. Can you have 32 valence electrons? Oh yeah, you can have a big range. You know, we can have 6 valence electrons. We can have 38 valence electrons. So be comfortable with, you know, a wide range of numbers. You're not going to have 150 valence electrons. If you've gotten to that, you've done something wrong, but, you know, probably going to top off around 32, 35, something like that. Okay, what do we do next? So this says distribute the electrons amongst the atoms, giving octets and duets to as many things as possible. And then hope it all works out. And then it's just perfect and balanced, right? And you're done. Okay, well, I find that the best way to do this always works. First, stick them together. You got to stick them together, right? I mean, if they're a molecule, they're stuck together. So let's give them each a bond. So I'm going to bond this thing and I'm going to bond this thing. Let's do the same thing over here with sulfur. We're going to kind of work both of these at the same time. So sulfur is in the center and there's 4 oxygens. So I'm going to bond each oxygen to the sulfur. Now, the next thing, you have to have 8 electrons. Okay, how many electrons are currently on the board over here? 4. We need to have 8. So you want to first make the outer guys happy, and then you work to make the inner guy happy. Don't include double bonds or triple bonds until every electron is on the board, if you need it. Okay, so leave double and triple bonds to the end. Neither of these will have a double bond or a triple. I will show you one though a little bit later. So let's make the outer guy happy first. So hydrogen, is hydrogen happy? Actually, hydrogen's already happy this way because it has that bond, which gives it access to 2 electrons. So hydrogen is good on both sides. So once you've made the hydrogen happy with either the duet or the octet, depending on what it is, then you need to go ahead and make the inner guy happy. So oxygen currently has access to 4 electrons. He wants 8 electrons. Okay, let's give him 2 more here, and then let's give him 2 more here, or 2 lone pairs of electrons. How many electrons are on the board? 8 electrons on the board. Okay, all the electrons are on the board. Now we just need to make sure everybody's happy. Hydrogens, we already said we're happy. What about oxygen? 2, 4, 6, and 8. He's happy as well, and we've made the Lewis structure. That's the ordering you want to follow. Let's do it for this guy over here. So I'm going to erase this, kind of start this fresh. So we said we have sulfur in the center, oxygens on the sides. There's 32 electrons to play around with. I'm going to stick it together first. Then I'm going to start to make the outer guys happy. And when I say happy, I mean get them enough electrons to become an octet. So this oxygen right here only has access to 2 electrons. He needs 6 more electrons. So I'm going to give him 6 more. This one as well needs 6. If you're thinking, oh my gosh, is she really going to like count all those electrons? Yes, I can look at it pretty quickly and decide that it is or isn't working. 2 here. There, okay, and then we'll add 6 more over here. Currently, there are 32 electrons on the board, so I like to give myself a check here when I've got all my electrons on the board so that I don't add or subtract any. Are the oxygens happy? Yeah, I mean, I filled them in a way to make them happy. So then we just need to check and make sure, is sulfur happy? Yeah, sulfur is actually happy. He has access to 2, 4, 6, 8 electrons. Everyone has an octet and they are happy. Now, because this is a polyatomic ion with a 2- charge, the last little fine tuning thing is just to put it in brackets and put a 2- charge on the outside. That just lets the reader know, because if you didn't put that on there, the reader is going to be like, well, why do you have 32 electrons? You should only have 30 electrons if it's sulfur and 4 oxygens. Where are the extra ones coming from? Well, they're coming from it not being sulfur tetraoxide, it's actually sulfate. And that is the system you follow. It will always work, at least for, you know, the ones that we're giving you. So what else do they say? If any atoms lack an octet, form a double or a triple bond, and we're going to do that. So let's do CO2, carbon dioxide. So first thing, actually I count my valence electrons before I do the skeletal structure. So I'm just going to count the valence electrons. So carbon is in column 4, so it brings 4. Oxygen is in column 6, so it brings 6, and we're going to multiply that by 2. So 12 plus 4, that gives us 16. 16 valence electrons to play around with. Now to make a structure that's balanced, I'm going to put the carbon in the center, and I'm going to put the oxygens on the side. What's the first thing we do? Stick it together, right? So let's bond them together. That takes up 4 electrons. Then who do we make happy first? Outer guys first, and then inner guys. If you try and fill the inner and work out, it will get messed up at times, okay? So always go outside in. So oxygen over here has 2 electrons, but he wants 8. So let's give him 6 more. Okay, this oxygen over here has 2 electrons. He wants 8, so let's give him 6 more. This is 8 plus 8 is 16 electrons. All my electrons are currently on the board. So let's check and make sure everyone's happy. Are the oxygens happy? Yes. Is carbon happy? No. Carbon only has access to 1, 2, 3, 4. How many does he want? He always wants 8. So, and this is an important thing. Some people will look and say, well, but carbon is in column 4, so doesn't he want 4 electrons? No, he brings 4 electrons. He wants 8 electrons. Make sure you know the difference. Oxygen brings 6 electrons, but they want 8 electrons. That's why they're coming together. Everybody wants more than what they are bringing to the table. So can I just do this? Can I add, oh, well, I'm just going to add 2 electrons like this. No, because I can only have 16 electrons. I already checked that off. That is not going to work. So what I have to do is I have to go and ask oxygen, you know, well, oxygen, can you help out a little bit? Can you take this and maybe move it over here? And oxygen says, sure, why not? So we make a double bond. Is that enough? Not quite. So carbon goes over to this oxygen and says, hey, can you help out as well? And that oxygen says, sure. And it makes a double bond as well. When you make a double bond, you have to erase the electrons that were in the previous spot. Otherwise, you're just adding more electrons. So make sure you erase. Whenever I make a double or a triple bond, I always recount and make sure that I still have the same number of electrons that I needed. So here I have 2, 4, 6, 8, 10, 12, 14, 16. I still have 16 electrons on the board. Is oxygen happy? Yeah, it didn't give the electrons away. It's just sharing them. So this oxygen still has access to 2, 4, 6, 8. This oxygen still has 2, 4, 6, and 8. And carbon now has 2, 4, 6, and 8. Everybody is happy. You made a double bond. So only double and only triple bond when you've put every single electron on the board and you've realized, oh crap, I'm still short. Any questions on that outside of like us doing some more practice with it? If you follow this system, you'll be able to draw Lewis dot structures for a good amount of elements. Good amount of molecules. Elements are easy to do. Let's see what they say here. Yeah, so this is the whole process of CO2, pulling it in to get a double bond. I want you to do the Lewis dot structure for cyanide, CN minus. Okay, this is 1 carbon combined with 1 nitrogen, and it has an overall minus charge. So I'll give you 3-4 minutes for that one. Okay, so let's look at cyanide. So first I'm going to calculate the valence electrons. Carbon has 4, nitrogen has 5, Now, if you just stopped there and added them together, you would get 9. And there are some that have odd numbers, but usually we're always in these pairs. So for the sake of this class, just make sure that they're not odd numbered. Or if you come up with something that's odd numbered, you're probably missing something. And in this case, you're missing the charge here, which means add another electron. So you should have 10 electrons to play around with. Now, it's just 2 things bonded together, so carbon and nitrogen. You could have done nitrogen and carbon. Doesn't matter in that case because it's a 3-dimensional structure, so it's just like rotating it. So I'm gonna stick it together, and then I'm gonna start making them happy. It doesn't really matter which one you pick, just pick one. I'm gonna start with carbon here. So he needs 8, he only has 2, so let's give him 6 more for a total of 8. Nitrogen needs 8, and I have 2 electrons to give to him. That's 10 electrons. We're done with adding electrons. We're not done with the structure though. Carbon's happy, nitrogen isn't happy. So we can't just add more electrons. Carbon has to share. So we're going to take away one of these and we're going to share it in the middle. Carbon still has access to 8. Nitrogen has access to 6. Is he happy yet? Not quite. So carbon needs to go ahead and share another to make a triple bond. All right. Carbon has access to 8. Nitrogen has access to 8. And there are 10 electrons on the board. The last thing, we can put it in parentheses and put a charge around it. If you start making double and triple bonds before every electron is on the board, it will not work. I mean, you may stumble across the right answer, but probably not. Okay. So let's do, are there exceptions to the rule? Always. Nitrogen sometimes has an odd number. Boron sometimes likes to have 6 instead of 8. Sulfur and phosphorus can do these things called expanded octets where you have like a lot of buddies. I will not test you on these. Everything you guys have will have duets or octets. There will be no expanded octets. I don't want to do resonance structures just yet. Let's do another one of these. I want you to do NH3 and then NH4 plus or ammonium. Keep these notes that you're taking because a lot of these are on your lab. Okay, the lab is all Lewis dot structures things. And so you may see some of these repeat. So you've already got them done. So I'll give you 5 minutes for that. Give yourself a couple seconds here to come back. Okay, so we've got two here. They're similar in that they both have nitrogen and hydrogen, but they have different structures. So this one over here, count up the electrons, 5 for the nitrogen plus 3, well, 3 times 1 for the hydrogen, or 3 for a total of 8 electrons. I'm gonna put nitrogen in the center and the hydrogens on the side. One reason, it looks more balanced. Second reason, hydrogen doesn't like to be in the center. Stick them together. Make the outer guys happy. Well, hydrogen is happy just with that single bond. Nitrogen is not happy, so I'm going to give him 2 more electrons. That puts 8 electrons on the board, and everybody is happy. This one over here, NH4 plus, so I have nitrogen, which is 5, plus hydrogen, 1 times the 4, plus actually means -1, right? If we're a plus charge, that means we're 1 down an electron. So you should have 8 electrons over here. Nitrogen in the center, 4 hydrogens on the side. And then we're gonna just stick them together. All right, from there, check and make sure the outer guys are happy, they're happy, nitrogen is happy, and there's 8 electrons on the board, and we're done. Okay, so 2 things that look similar but have slightly different structures. This one has got a lone pair of electrons here. This one, all of them are bonded. That will have an effect on its shape. So one more thing I want to talk about are resonance structures, or sometimes they're called equivalent Lewis dot structures. So let's look at SO2. So here we have sulfur, which contains 6, or brings 6 valence electrons, plus oxygen, which also brings 6, and there's 2 of them. So we have a total of 18 electrons to play around with. I'm going to draw a structure that is sort of balanced looking. So sulfur in the center, oxygen's on the side. I'm going to stick it together like this. Then I'm going to make the outer guys happy. So oxygen is going to get an additional 6 for 8 with the bond. This oxygen is going to get 6 to have 8 with the bond. And then that's 16 electrons on the board. I need to have 18 electrons, and sulfur isn't happy yet, so I'm going to put 2 electrons right here. So that gives us the 18 electrons on the board. The oxygens are happy. The sulfur is not happy yet, but I don't want to give him 2 double bonds because that would be too many. He just needs 2 more electrons. So if we consider this oxygen 1 and this oxygen 2, where does he get his double bond from? He could take it from here, or he could take it from here, but he can't take it from both at the same time. So let's say we're going to take it from here. So we get a structure that looks like this: double bond, sulfur, single bonded to this oxygen over here. Looks something like this. Well, but what if we wanted to take it from the second one? Or it could look something like this: sulfur, single bonded to the first one, and double bonded to the second one, like this. Anytime you get into a situation where you need to make a double bond, but you can't make it on both of them, and it doesn't really kind of matter which one you pick, that's known as a resonance structure. Resonance structure. What's actually happening with this resonance structure is they both are sort of simultaneously existing. So it's kind of like a 1.5 bond that's happening on each side. Sometimes it's drawn with a double bond on one side and then like a dotted line here to let you know that it's sort of like happening on both, but in a halves equality. So the drawings here are a little bit better, but we get this thing here where either one is sort of existing. There's sort of an intermittent between those two. Anytime that happens, you have a resonance structure. So with that being said, do the Lewis dot structure for carbon 8. CO3 with a 2- charge. I'll give you 3 minutes for that. All right, so carbonate is a polyatomic ion. So we need to take that into account with the charge. Hopefully you drew a resonance structure since that's what we're talking about. If not, we'll go over it. So carbonate is 6 plus oxygen, which is 6 times 3. So what, 24 plus 2. I know, minus, but it means plus. We're adding 2 electrons. So 26 electrons. Carbon goes in the center, oxygen's on the sides. Stick them together. Then let's make the outer guy happy. So, oh, I did something funky there. Hold on, I don't like something I did there. 26 seems like too much. Carbon doesn't have 6. Carbon has 4. Yeah, let's change that up. So 18, 19, 20, 21, 22, 24. Is that making you guys happier? Yeah, at least James. Okay. So Well, 18. Oh, well, we might actually, yeah, no, we will have a resonance structure. Yes, we will. Okay, so oxygens need 6 more. That's 24 electrons on the board. The oxygens are happy. Carbon isn't happy yet. You look, he only has access to 2, 4, 6. So carbon needs 2 more electrons. Which one do you pick? I mean, I'm just going to pick this one over here. We'll get rid of these. And I'm going to put it right there. Okay. If you would put it here instead, that's fine. But the key here being that it's a resonance structure. Again, sometimes it's drawn with like a dot, 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 or a dash to let you know that you could have picked any of them. What I don't want you to do is this. You put carbon, okay, let's. And you're like, go double bond crazy. You're like, okay, well, I'm gonna put a double bond here. And I'm gonna put a for sure double bond here. And I'm gonna put a double bond here on all of them. Why does that not work? I mean, you still have 24 electrons, the oxygens are happy, but look at carbon, oh my goodness, you've saturated him. 2, 4, 6, 8, 10, 12, too many, only wants 8. So we don't like this, we like this. Any questions on Lewis dot structures? Because we're going to move forward to kind of putting this into 3-dimensional space. And if you can't do the Lewis dot structures, you can't really do the next thing. So does anybody have any questions on that system, on where I'm getting those numbers from, on why it's the ordering it is? Okay. So let's move into the second theory that we have, which is called the VSEPR theory. Or VSEPR stands for valence shell electron pair repulsion theory. This theory is based on the idea that electron groups, and an electron group can be a lone pair of electrons, so that would be 2 electrons that are in their lone pair, a single bond. It can be a double bond, it can be a triple bond. It's an area where you have electrons that they like to repel each other because they're negative. So they're going to try and get as far away from each other as they absolutely possibly can. The repulsion between these negatively charged electron groups that are specifically on the central atom determine what the shape of the molecule is going to be. Okay, so however many of these groups you have around the central atom, it will spread out in different ways. So think about having an electron in the center, and then you've got all these ropes coming off of it. And if you have 2 ropes or 2 electron groups, it's going to have a specific shape. If you have 3 ropes, it'll have another shape. 4 ropes will have its own shape too. So let's look at some of these shapes. The simplest one is the linear geometry. Okay, so it's known as linear if you have 2 electron groups on the central atom. You may be saying, well, no, but aren't there 4 electron groups on the central atom? No, we consider a double bond to be 1 electron group, 1 area where the electrons sit. Okay, can you break up a double bond? No, they're sealed off here and they're sealed off here, right? So that's 1 unit. This is another unit. So there's 1, 2 electron groups. Remember, an electron group, and this, people always have trouble with this, but I'll write it out here. What is considered 1 electron group? 1 electron group can be a lone pair. It can be a single bond. It can be a double bond. It can be a triple bond. These are all lone examples of one electron group. So a lone pair would look like this, dot, dot. A single bond would be a bar, a double bond would be 2 bars, and a triple bond would be 3 bars. All of those are classified as one electron group. Triple bond is not 3 electron groups. Okay, it's fused together. So going back to this slide, we've got 2 double bonds or 2 electron groups. Kind of looks like this, right? Here's a double bond here and here's a double bond here. How far apart can those 2 electron groups get in 3-dimensional space? They can get 180 degrees away from each other, right? Is there any way for them to get farther than that? Well, no, if they get farther on this side, they're closer on this side. So that is the absolute farthest they can get away from each other. The 180 is why we call this structure linear. So anything that has 2 electron groups are going to give you a linear structure. If you want to make this at home, put a marshmallow with 2 sticks on the side and 2 marshmallows on the other side. That's what that structure looks like in a straight line. Let's make it a little bit more complicated. What if instead of What if instead of 2 electron groups, we have 3 electron groups? So here we've got carbon in the center. And it has 3 things coming off of it. It's got a single bond here that's considered 1 electron group, a single bond here, which is considered another electron group, and the double bond is considered the 3rd electron group. Double bonds are 1 electron group. Why don't we include these in the shape? It only matters the electron groups on the central atom. Electron groups or lone pairs on the outer guys doesn't affect the shape. Because look at here, look at how the shape is happening. The 2 that are here aren't going to do a whole lot. Okay, they're on the edges. It's what's happening from the center. So if you have 3 electron groups, that means you've got 3 ropes hanging off of this central atom. How can those ropes get as far away from each other as they possibly can? Well, they can make this geometry, which is called trigonal planar. Planar because it's in one plane, like a pizza. Trigonal because it's broken into 3 quadrants. So each bond angle is 120 degrees. It's like taking a big pizza and cutting it into 3 slices. So you have 3 electron groups on the central atom, you will have something that's trigonal planar. All right, what if you have 4 electron groups like CH4? This is what the structure would look like in 2-dimensional space, right? You've got carbon in the center and you've got 4 hydrogens around it. But remember, we are working in 3-dimensional space. So these 4 groups can actually spread out farther than 90 degrees, right? On this structure, it looks like it's 90 degrees, but we can actually move forward and back in space. The most efficient way to get these electron groups away from each other is to form what's called a tetrahedral. So this is tetrahedral geometry. It's a little pyramid, right? So you'll have your carbon in the center. 4 of the hydrogens will point sort of slightly down and the other one will point up. The bond here is 109.5. These are farther away than the 90. Now, when you're drawing it on paper, you're going to draw it like this, but we're going to assume it looks like this in 3-dimensional space because they're going to have their chance to spread out. Any questions on those 3 geometries? No? Okay. Let's look at annotate still on? Right, well, we'll just redo one. So let's look at, you had NH4 plus. Remember back in your notes, this was 8 electrons. So we put nitrogen in the center, hydrogens on the sides. We're going to stick it together. Okay, what is this structure's electron geometry? Look at the central atom. How many groups do you have? 1, 2, 3, 4. 4 equals tetrahedral. A little tetrahedral shape. It's very similar to that little methyl that we drew. What about our carbonate? CO3 2 minus. You should already have it in your notes. It was carbon, oxygen, oxygen, oxygen. Stick them together. And then I'm going to make this one the double bond. What is this structure? How many electron groups do you have on the central atom? 1, 2, 3. Trigonal. That's where I can write trigonal planar. 3 groups, trigonal planar. What about, trying to think of something. That'll give me a similar structure. Can't think of anything right now. I was going to say CO2, but we've already done CO2, which is linear. So now you can take your Lewis dot structures and you can start layering what the 3-dimensional shape looks like. Does it get more complicated than this? It does. Because what happens when you have a lone pair of electron? So NH3. We drew this earlier. NH3. It looks like this. Nitrogen, hydrogen, hydrogen, hydrogen. Stick it together. But then we have a lone pair of electrons on the top. A lot of times people want to say, oh, this is trigonal planar, right? There's 3 groups, but there's actually not. There's 4 groups. 1, 2, 3, 4. So when we've got lone pairs of electrons, we need to start to separate out, are we talking about the electron geometry or are we talking about the molecular geometry? The electron geometry is the geometric arrangement of the electron groups. So how many electron groups do you have? You just go with that. So this thing has 1, 2, 3, 4 electron groups. So it's tetrahedral because that's how many of electron groups it has. But we also have this thing now called molecular geometry. This is the geometrical arrangement of the atoms. So we're looking just at the atoms. So if I look at just the atoms, I kind of have to ignore the lone pair on top. Think of your tetrahedral shape and take the top of the pyramid off. What do you get left with? You're left with 3 atoms that point slightly down, or it looks like this. Sometimes people want to just default and say, oh, well, that's trigonal planar. But is this planar? Are these 2 things in the same plane? No, it's not flat like a pizza. It points down because the lone pairs push down on those. So it actually has a molecular geometry known as trigonal pyramidal. Now, going back to those ones that we had talked about before, like this guy here, it has an electron geometry and a molecular geometry that's both tetrahedral. So the electron geometry here is 4 electron groups, so it's tetrahedral. Its molecular geometry is the same because it doesn't have any lone pairs. So every bond also has an atom. So the atom shape follows the electron shape. So it's also tetrahedral. Same thing with this carbonate. Oopsies. Carbonate has 3 electron groups, but every electron group is also attached to an atom. So the electron group geometry and the molecular group geometry parallel each other. So they would both be trigonoplanar. The only time that it's different is when we get those pesky lone pairs of electrons, because one of the groups doesn't have a buddy, so they can't mirror each other. Water is another example of this. Let's revisit the structure of water. H2O, oxygen in the center, hydrogens on the sides, bond, bond, 2 lone pairs here. So what is the electron geometry? Remember, electron geometry is asking you just about how many electron groups you have. So we have 1, 2, 3, 4. 4 electron groups, so our electron geometry should be tetrahedral. Now this is where it gets tricky, the molecular geometry. What is the molecular geometry? So we have to think about the shape of the original tetrahedral, but we rip 2 of the atoms off. So in your mind, like even if you have to close your eyes, visualize that tetrahedral shape, rip 2 of the atoms off. Are you left with a linear straight structure? No, these 2 things are pushing down. Let's look at I can't really draw them because I'm not good at that sort of stuff, but look at this. So here's our tetrahedral shape. These are lone pairs, so kind of ignore those. What's left is oxygen with these 2 H's pointing off in a direction, or we get what's known as a bent structure. So the molecular geometry for this is bent. Sometimes it's called V-shaped as well. We can add that over here. Molecular geometry is V-shaped or bent. So there can be a lot of structures that are tetrahedral, but then their molecular geometry is something different. How many geometries are there? There are way more than what we're talking about right now. This diagram shows you all the possibilities that you will be responsible for. So this may be something that's helpful. Oops. This may be something that's helpful for you when you're taking your test. How many electron groups do you have? Then separate them into things that are bonded and if there's lone pairs. If there's no lone pairs, the geometry is the same, right? Those are the easy ones. If you have one of those lone pairs, that's where you have a difference in your electron geometry and your molecular geometry, because the lone pair is pushing on the other group, affecting its shape. So this could be super useful when trying to come up with all the electron molecules. So when determining the shape because of VSEPR, first you're going to draw the correct Lewis dot structure. If you can't draw a Lewis dot structure, you're going to have a hard time with this. Determine the total number of electron groups around the central atom. Determine the number of bonded groups, and if there are any lone pairs, and then reference the table. And that's what you're going to do. So let's, you want to do a couple of these on your own? We'll do 1 or 2 of them, and I'll have you tell me what I want you to draw the Lewis dot structure. I want you to tell me what the shape is, both electron and molecular. Hold on 1 second, let me grab. We'll do 1 or 2 that are on your lab so you don't have to, or so that you can use this information later. These ones are a little bit harder for me to just take them out of thin air, so let me. Oh, come on. Okay, great. So CF4, I want you to do the Lewis structure. I want you to tell me what the electron geometry is and the molecular. Sometimes these are the same, okay? Sometimes they're not. So you'll do it for CF4, and then I also want you to do it for H2S. Same thing, Lewis structure, electron geometry, and molecular geometry. I'll give you all 5 minutes for that. let's come back together. So this one over here, CF4. So the first thing is to do the Lewis dot structure. Carbon has 4, fluorine has 7 times 4 for a total of, what is that? 28, 30, 32. So carbon in the center, fluorine, 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 fluorine. Stick it together. Then we're going to fill in the outer guys. Giving each of them access to 8 electrons. There's 32 electrons on the board, and everybody is happy. Carbon has the 4 bonds, all the other guys are happy. So what is the electron geometry? That talks about the number of electron groups. I have 1, 2, 3, 4 electron groups around the central atom, so that makes it tetrahedral. Do I have any lone pairs on the central atom? No, everybody is paired, so these two things get to mirror each other, so this is also tetrahedral. Sorry, my handwriting is especially bad today. Okay, this guy over here, H2S. So hydrogen brings 1 and there's 2 of them, and sulfur brings 6 for a total of 8 electrons. I'm gonna put sulfur in the center and hydrogens on the sides, and we're gonna smush them together. Then we wanna make the outer guys happy. Are hydrogens happy the way they are? They're so happy. So sulfur gets the rest of them. 2 there and 2 there. If you did 2 here and 2 here, that's okay too. Remember, it's a 3-dimensional space, so we can rotate it around. What you don't want to do is when you draw it like this though, start to think, oh, that looks linear, that looks straight, because that's not what's happening. So our electron geometry. Well, we got to figure out how many electron groups do we have? 1, 2, 3, 4 electron groups, tetrahedral. So these both have the same electron geometry. The molecular geometry is different though. Where this one, every bond has a buddy. Here, well, 2 of the bonds have a buddy, 2 of them don't. So think of your pyramid shape. Rip a top one off and a side one off. What are you left with? You're left with this sort of wonky bent shape. Bent. If you're like, I can't visualize it, just go to the diagram, right? And use the diagram to figure out what those are. Okay, one other thing here I want to talk about. Actually, no, we'll stop there. We'll finish this up on Thursday. We did a good amount today. So Thursday will be this stuff, and then we will actually lecture a little forward into chapter 6. That won't be on this test. It'll be on the following test. Do make sure you're scheduling some time for yourselves to take that test sometime Sunday through Tuesday. Otherwise, you are all good to go. Enjoy the rest of your day. Over here, it looks like the sun's come out for a second, so I'll try and go for a walk. So maybe get outside, and then I will see you all on Thursday. All right, bye guys. Thank you.